All right, let's find this flux integral. So again, as always, this will be E dot the unit normal for the surface, and then we can just do a surface integral. We're actually going to do it in pieces, first with M1. So on M1, my unit normal, again it's outward, will be x, y, z over the radius, which is 3. And so E dot n is just going to be 4x, 4y, 4z dot xyz over 3. And that will equal 4x squared plus 4y squared plus 4z squared over 3. So my integral will be, and notice of course the normal is upward for outward. All right, so our integral is going to be E dot the unit normal. 4, let's do x squared plus y squared plus z squared all over 3 ds. Well, everywhere, whoops, should call this M1. Everywhere on M1, that is a constant, right? So M1 is the upper hemisphere, and so I can put a 9 in here. So this will just be integrate over M1, 4 times 9 over 3. And well, that'll equal 12. I'll factor that out. And now we're just integrating 1 ds. So this will just be 12 times the surface area. I guess I'll put this way. Surface area of M1. Well, we might know the surface area of a sphere. A full sphere is 4 pi the radius squared. So for a hemisphere, it'll be half that, so 2 pi. So times 2 pi times the radius squared. So we get 18 times 12. So 180 and 36. 6 cubed pi. Okay, so if we're lucky enough to get a constant for our surface integral, and we know the surface area of the shape, then we can just proceed that way. Again, we can do this here, but we can't do it on triple integrals, but for us, everywhere on M1, that quantity is the same. All right, now on M2, we want this flux integral. Well, M2, it's the bottom of this. You want a closed surface. If I have outward normals, this normal is pointing in the negative k direction, right? It has to be a unit vector. So n, oops, unit normal, be 0, 0, negative 1, or negative k. So E dot n is going to be 4x, oops, 4y, 4z dot 0, 0, negative 1. And that'll just give me negative 4z. So now I want to integrate on M2 4z ds. I could parameterize the surface if I want. I mean, there is a way to parameterize this disk, but note that everywhere z is 0, right? This is the bottom here. So we're in the xy plane. So everywhere on M2, z is 0, so we would just end up integrating 0. And so we'll get 0. And then the flux through the whole amount then is 216. Right? You just add the two. So the flux through the whole closed surface pictorially, we have a radial vector field, and so here it's at the equator, all the vectors point radially outward, which means none are going through that surface. I don't know if you can picture that, but that's the way it is. All right, so there's that problem.